Okay, so here we go. One of my favorite websites is this one that's got 33 million views to it. It's this young man here who I met at a physics conference this past year, and he's gotten all kinds of awards for his innovative physics teaching and things like that. But here is a interesting thing. Now we're going to not include air resistance right now until we get to drag a little bit later on in the semester, okay? And then we'll add air resistance. But right now, we're just basically things are going to fall, and that's just the way it's going to be. But watch what happens. Watch this. This is pretty amazing stuff.
And went to the Gordon Dam in Tasmania, which is 126.5 meters or 415 feet high. Then they dropped a basketball over the edge. You can see that the basketball gets pushed around a bit by the breeze, but it lands basically right below where it was dropped. Now watch what happens when they drop another basketball, but this time with a bit of backspin.
Whoa, look at that go! It's incredible.
You want those to get back in the water, do you?
This is Brett who just threw it. I literally just dropped it with a bit of spin, like I didn't even throw it, and it just took off. Like we had no idea that was going to do that.
And this is where I come in. The basketball was subject to the Magnus effect, which affects all rotating balls or cylinders as they fly through the air. And it works like this. As the basketball picks up speed, air on the front side of the ball is going in the same direction as its spin, and therefore it gets dragged along with the ball and deflected back. Air on the other side is moving opposite to the ball spin, so the flow separates from the ball instead of getting deflected. The net result is the ball pushes air one way, so the air applies an equal force on the ball the other way. And this is known as the Magnus effect, named after Heinrich Gustav Magnus, who described it in 1852. Of course, Isaac Newton beat him to it by nearly 200 years, describing the flight of tennis balls at Cambridge College. But, he's got enough stuff named after him. This effect is very important in sports like tennis, soccer, and golf. But could it have non-sport applications? Perhaps. This is a sailboat. I know it doesn't look like a sailboat, but those aren't chimneys. They are spinning cylinders called Flettner rotors, and they take the place of the sails. They deflect crosswinds using the Magnus effect to propel the ship forwards. And this is a plane with spinning cylinders instead of wings. Using the Magnus effect, the cylinders actually generate more lift than traditional wings. However, they also generate way more drag, making them impractical. This plane only flew once, and then it crashed. But the Magnus effect is making a comeback. Here is an experimental rotor wing aircraft, which generates all its lift from spinning cylinders. And this is the E-Ship 1, which uses 4 spinning cylinders, that's 4 Flettner rotors, to increase its efficiency and reduce the amount of diesel it burns. So in the future, the Magnus effect may help more than just basketballs fly.
Oh, look at that go!
All right.
Now the real reason my friends from How Ridiculous were at the dam was to set the world record for the highest basket ever scored. So go check out their channel and the video and subscribe to them for more epic trick shots.
Okay. All right. So we can get to those a little bit later. But anyway, it's a great website if this physics stuff is starting to kind of rock your world a little bit, and I hope it is. But anyway, let's get down to the brass tacks of why you're here. All right, so let's talk about. Let's just start from the current slideshow. All right, there are many types of potential energy. We will begin by focusing on gravitational potential energy. Okay, so this suitcase is up here. Bam. It will come down as long as we are here close to Earth, where the potential energy is equal to the mass of the object times the acceleration due to gravity, not in the negative, because this is a magnitude type thing, and where we get our positive and negative is from the height. So H final minus H initial, 0 minus, let's say 2 meters is -2. That would be a loss of potential energy. Okay, that would be a loss of potential energy. So there you are. H is the object's height above the Earth's surface, or an arbitrary. Now, if they're up in an airplane, they could be way above the Earth's surface, but we're just taking from here to here. We're taking from 30,002 feet and 2 meters down to 30,000 meters. You subtract the 2, you still get the delta 2. Doesn't matter. Okay? Potential energy example, the height of an Olympic diver. All right? Let's go ahead and calculate the potential energy of a diver standing on a platform where the diver has a mass of 81.8 kilograms. All right? So let's just do that. Let's get out of this. Let's escape here. Do my escape clause. Let's put, oh, you already saw the calculation. Oh, well, but that's okay. But these are lesson 8 notes. All right, I don't want to, shoot, I already forgot, what did it say, 81 kilograms? So the mass was 81 kilograms. G is 9.8 meters per second squared. Now with my 210 students, I'm really a stickler. Is it positive or negative? Because if they're doing the vectors and the falling and all that kind of stuff, if they use this as an acceleration and not just, well, it is an acceleration. It's the force times the distance. And the height, is 10 meters. So we do it in, we kind of fudge a little bit on it because we're just trying to get the big ideas of the stuff. Is equal to mgh. So you just multiply that out. And I'm going to go ahead and, well, I'll just plug it into my calculator here. Why not? Oh, so I've screwed up already. 81 times 9.8 times 10. Boom. 7,938. And its energy, joules. All right. They probably put 7,900 here, maybe. Let's take a look. What did they say? Oh, 81.8. Oh, okay. So you see, I'm off a little bit because I didn't put the 0.8 in there. Makes it, but on your homework, I always add or subtract. I have a plus or minus fudge factor of about 5 or 6% from what the actual answer is supposed to be. All right. So that's good. All right. So now let's take a look at this. Let's take a look at this Mobley and Pats. That's your next track, okay? So out here on this one,